Blow a soap bubble. Go ahead. Picture it. You dip that little wand into the dish soap, you blow, and out comes this perfect, shimmering sphere floating through the air. Beautiful thing. Everybody's done it. Kids love it. Adults pretend they don't love it, but they do. Now let me ask you something that sounds so simple you might laugh. Why is it round? I don't mean sort of round. I mean perfectly, mathematically, flawlessly round. Not an oval, not a lumpy blob. A sphere. Every single time. You never blow a soap bubble and get a cube. You never get a pyramid. You get a sphere. Why? Well, you might say it's surface tension. Fine. Good answer. But that's a name, not an explanation. Saying surface tension is like saying a ball rolls downhill because of gravity. Sure, but what's actually happening? What is the soap doing? Molecule by molecule, and why does it end up as a sphere every single time? As if it attended a geometry lecture before you blew it out of the wand. Here's what's happening. The soap film is made of water sandwiched between two layers of soap molecules. Those soap molecules are amphiphilic, meaning one end loves water and the other end hates it. They arrange themselves with their water-loving heads pointing inward toward the water layer and their water-hating tails sticking outward into the air. This arrangement creates a stable film, but that film has energy. Surface energy. And every molecule in that film is pulling on its neighbors, trying to contract, trying to shrink the surface down. The soap lowers the surface tension compared to pure water, which is why you can make a bubble at all. Pure water has too much surface tension to form a stable film. But the film still wants to be as small as possible. It's pulling inward from every direction, equally at every point. And the shape that encloses a given volume of air with the least possible surface area is mathematically a sphere. The ancient Greeks suspected this. It took until 1884 for the German mathematician Hermann Schwarz to prove it rigorously. But the soap bubble doesn't care about the proof. It just does it. Instantly, every time. No computation, no hesitation. It inflates, it wobbles for a moment, and then it settles into a perfect sphere, as if it had known all along where it was headed. All right, so that's cute. A bubble is round. Big deal. You already knew that. But now let me change the game a little. Instead of blowing a free-floating bubble, I'm going to take a piece of wire and bend it into a shape. Let's start easy. Bend the wire into a circle. Dip it in the soap solution. Pull it out. What do you get? A flat disc of soap film stretched across the circle. The flattest, smoothest surface you could imagine. And it makes sense, right? A flat disk has less area than any other surface you could stretch across a circular boundary. It's the minimal surface. The soap found it. Now bend the wire into something more complicated. Make a helix like a slinky with a straw connecting the ends. Dip it in. Pull it out. And what you get is part of a surface called a helicoid, this beautiful twisting ribbon-like thing. Or bend the wire into a square frame. You don't get a flat square. You get a surface that dips slightly inward, curving like a saddle, because that saddle shape actually has less area than a flat square would. The soap found the better answer. Now make the wire really weird. Twist it into some irregular asymmetric three-dimensional tangle. Dip it in. Pull it out. And the soap film stretches itself into this gorgeous flowing surface that hugs the wire at every point. It curves and dips and sweeps in ways that look almost artistic, like a sculpture. But it's not art, it's physics. That film has found in a fraction of a second the surface of minimum area that spans that wire boundary. This is a famous problem. It's called Plateau's problem, named after a Belgian physicist named Joseph Plateau, who devoted his life to studying these films in the 1830s and 40s. And Plateau's story is itself remarkable. He'd permanently damaged his eyes by staring at the sun for 25 seconds during an optics experiment. Think about that. 25 seconds of staring at the sun in the name of science. By 1843, he was completely blind. But he kept working. He kept experimenting. He had his family and his colleagues describe to him what the soap films were doing, and he ran his fingers along wire frames to understand the shapes. And what he discovered was extraordinary. He found that soap films don't just make pretty shapes. They follow rules, strict, precise geometric rules that never get broken. Not sometimes, not usually, always. Here's the first one. When soap films come together, they don't just crash into each other at random angles. 3 films always meet along a line, an edge, and they meet at exactly 120 degrees. Not 119, not 121, 120 degrees. Always. Plateau called these edges, where 3 films meet plateau borders, and the angle is always the same. No matter how complicated the frame, no matter how tangled the wire, no matter how many films are involved. 3 at 120. And here's the second rule. When those edges, those lines where 3 films meet, come together at a point, exactly 4 of them meet. And they do so at an angle of about 109.47 degrees. That's the tetrahedral angle. The angle you'd get if you put a dot in the exact center of a tetrahedron and drew lines out to the 4 corners. 4 edges meeting at one point at tetrahedral angles. Always. No other configurations are stable. This is the remarkable part. Let me show you what I mean. Take a wire frame in the shape of a cube. 6 faces, 12 edges, 8 corners. Dip it in soap. Pull it out. You might expect 6 flat films, 1 for each face of the cube, meeting at right angles along the edges. That's the symmetrical, obvious configuration. But that's not what you get. What you get instead is this intricate, sculpted shape with 13 distinct film surfaces. The films curve inward. They meet in groups of 3 along edges at 120 degrees. And near the center of the cube, there's a small, slightly warped square where the plateau borders converge. It looks nothing like a cube on the inside. It looks like architecture from another world. If you somehow manage to force 4 films to meet along a line at 90-degree angles, the way the walls of a room meet at a corner, the configuration would not hold. It would snap instantaneously. It would rearrange itself into 2 junctions of 3 films, each junction at 120 degrees. You can watch this happen in real time if you're careful. Build the unstable arrangement, and before you can even pull your fingers away, it pops into the stable one. The 4-way junction at 90 degrees has more total surface area, more energy, than the pair of 3-way junctions at 120 degrees. And the film finds the cheaper arrangement faster than your nervous system can register what happened. Why 120? It's not that nature has a preference for pretty numbers. It's that 120 degrees is where the forces balance. Think about it physically. Each film is under surface tension, pulling the junction toward itself, trying to shrink. When 3 films meet, you've got 3 pulls acting on the junction line. The only arrangement where all 3 pulls exactly cancel out, where the junction doesn't get yanked toward any one film over the others, is when the 3 films are equally spaced at 120 degrees. Each pull gets opposed equally by the other 2. Perfect balance. It's the same reason that if 3 people are pulling equally hard on ropes tied to a single ring, the ring will stay put only if the ropes are aimed 120 degrees apart. 2 people pulling in nearly the same direction would overpower the third. Any arrangement other than equal spacing means unbalanced force, which means the junction slides, which means the configuration isn't in equilibrium. And the tetrahedral angle at corners, 109.47 degrees, is the same idea in 3 dimensions. 4 equal forces pulling outward from a single point balance out only if they point toward the 4 corners of a regular tetrahedron. That's the most symmetric arrangement of 4 directions in 3-dimensional space. So when 4 plateau borders meet at a point, the tetrahedral angle is the only stable option. Now this is already pretty remarkable. A thin film of soapy water, something a child makes in the backyard on a Saturday afternoon, is solving a geometry problem that stumped mathematicians for over a century. Plateau described these rules from his experiments in the mid-1800s. But proving that these rules followed necessarily from the mathematics of minimal surfaces, that they were the only possible stable configurations, that took until 1976, when a mathematician named Jean Taylor nailed it down using a branch of abstract mathematics called geometric measure theory. More than 100 years of effort by serious mathematicians. And the soap film had the answer the whole time, just sitting there on the wireframe waiting for someone to notice. But all right, I can hear you thinking. Fine, the soap film is clever with surfaces and angles. So what? It's just doing what physics tells it to do. Water flows downhill too. Nothing really surprising here. So let me add another layer. Let me give you a puzzle. Imagine you've got 3 towns arranged in a triangle. Let's call them Town A, Town B, and Town C. You need to build roads connecting all 3 towns so that you can drive from any one to any other. And you want to use the least total road possible. You're on a budget. Every mile of road costs money, and you want to minimize the total. Most people's first instinct is simple. Connect each town to the other 2. Draw the triangle, 3 roads along the 3 sides, done. But that uses too much road, because you've got redundant connections. You don't need all 3 sides. Okay, so what if you just pick 2 of the 3 sides? Say the 2 shortest ones. That guarantees every town can reach every other town by traveling along at most 2 roads. And the total road is shorter, better. But there's an even better solution. One most people don't think of. Instead of just connecting the towns directly to each other, you add a new point somewhere in the middle. A junction, an intersection, and from that junction you run 1 road to each of the 3 towns, 3 roads radiating out from a central hub. If you pick the right location for that hub, the total length of road you need can be shorter than any combination of the sides of the triangle. Where is the right location? This is a problem that goes all the way back to Pierre de Fermat, the great French mathematician who posed it around 1643. He didn't solve it himself. He sent it as a challenge to the Italian mathematician Evangelista Torricelli. And Torricelli, a brilliant man who also invented the barometer, figured it out. He constructed equilateral triangles on 2 sides of the original triangle, drew lines from the new vertices to the opposite corners, and found that those lines crossed at a single point. That point is the optimal junction, the one that minimizes the total distance to the 3 towns. And here's the key property of that point. If you stand at the Fermat point, as it's now called, and look toward Town A, then turn to look at Town B, the angle between those 2 directions is exactly 120 degrees. Turn from B to C, another 120 degrees. From C back to A, another 120 degrees. 3 roads, radiating from a single point, equally spaced at 120 degrees. There's an important caveat. This only works if all the angles of the triangle formed by the 3 towns are less than 120 degrees. If one angle is 120 degrees or more, the Fermat point lands right on the vertex of that large angle. There's no benefit to adding a junction point. You just connect the other 2 towns to the obtuse angle vertex directly. The soap film handles this case perfectly too. When you dip the 3 pins, and one of the triangle's angles exceeds 120 degrees, the film stretches directly from that pin to the other 2. No central junction, it just knows. 120 degrees. Where have we seen that number before? The soap film. When 3 soap films meet along a line, they meet at 120 degrees. It's the same number. And it's not a coincidence. You can actually solve Fermat's problem with soap. Take 2 parallel sheets of clear glass or plastic. Drill 3 pins through both sheets, perpendicular to the surface, positioned at the locations of your 3 towns. The pins bridge the gap between the 2 plates. Now dip the whole sandwich into soapy water. Pull it out. The soap film stretches between the pins, forming thin vertical walls. and those walls arrange themselves into exactly the minimum network connecting the 3 points. 3 walls meeting at a central junction at 120 degrees, the Fermat point. The soap found it. Instantly. No compass, no equilateral triangles, no construction lines, no Torricelli. It just settled into the configuration of least surface area, which, because the film is stretched between 2 parallel plates, is equivalent to the configuration of least total length. And there it is, shimmering between the pins. The answer to a problem posed by one of the greatest mathematicians who ever lived, solved by a bit of dishwater and air. If you've never seen this done, let me tell you what it looks like in person, because the experience is more striking than any description. You dip the frame. You pull it out. And at first, the film is messy. It's attached to everything, forming closed bubbles and extra surfaces between the plates. You blow gently on the excess film, or pop it with a dry finger. And then, as the extra surfaces are removed, the remaining film snaps into position. You can see it happen. 3 thin vertical walls, stretching from one plate to the other, meeting at a point in the middle. The junction is sharp, clean, perfect. The angles are so precise that if you measured them with a protractor, you'd get 120 degrees to within the accuracy of your instrument. There's something almost eerie about watching it. You know that behind this simple physical event is a mathematical theorem, a proof by Torricelli, centuries of geometric reasoning. And the soap just does it, without any of that machinery, without any knowledge. It does it the way a stone falls, not because it understands gravity, but because gravity acts on it. The soap film doesn't understand minimization. Minimization acts on it, and the result is the same answer that all that mathematics produced. Let that sink in for a moment, but I'm not done. I haven't even gotten to the hard part yet. 3 towns is nice. Torricelli handled 3 towns. You can even do it with pencil and paper if you're patient. But what about 4 towns? Or 5? Or 10? Or 100? This is the generalization, and it's called the Steiner tree problem.